Good morning, students.
Good morning, ma'am.
Yeah, you are able to see my screen, Amrish?
Yes, ma'am.
Yes, very good. So today's class, the last class, we were talking about case-based reasoning. So we have come to the fag end of this module 5. So we are just left with one more concept that is called as reinforcement learning. So today's class, we'll be learning what exactly we mean by reinforcement learning. Okay. Now, let us consider how we can build a. We are all in case of machine learning. We have been talking about how to train the machine so that the machine can predict something, right? So now here we are going to learn how if we have to build a robo which wants to learn. Okay, so let us call it as we want to build a learning robo. That means what you so far what we have seen from module 1, we have been seeing how we can train the machine so that it can predict something, right? Today we are going to see how we can train a robo, how we can train a robo where that robo can learn. This robo we will also call robo as a, can be called as a agent. Now this is what we'll be learning in reinforcement learning. How if we are trying to consider training a robo or building a learning robo is called also as a agent, then how do we go about it using this concept of reinforcement learning, right? Now this robo, or I said I'm also calling it as agent. Okay, now this any robo, as all of us know, will have some sensors, right? Why does it have some sensor? Can you answer me? Why does it have some sensors? What is the use of these
Ma'am, to
sensors?
respond.
Yeah, either we can say it is responding, or we can say it is requiring, it requires sensors to observe, right? It has to observe the environment, or observe, we'll say observe the state of the environment. Suppose I have a robo here, it will have to observe, no? It has to see what all is there around its environment or around its surroundings, what all is there in that particular place. It has to see. How does it see? How does it observe? It observes using the sensors, right? Next, what else it will have? It has to perform certain actions. So it will also be involved in performing a set of actions. So why it has to perform? In order to alter the state. So it will not be in the same state, right? It will observe, it will take some action, it will move from one state to another state. Suppose it is moving. So before it moves, it is in some initial state. It takes some action. What is the action there? Movement. Movement is an action. Once it moves, what is happening? There is a change in the state, right? So as I said that we are going to consider building a robo. When I say building a robo, building a machine, that means you are going to train a robo actually. That is what we are learning here. That is our example that we are considering. So this robo is also can be called as an agent. Now this robo is consisting of, as all of us know, it consists of sensors and it consists of some set of actions. Okay, now sensors means why sensors are required. Sensors are required so that it can observe the state of its environment, in what state it is right now. Based on that, it will take some action. When it takes some action, the state is going to get altered. Okay. Now, for example, let us say a robo may have sensors. Let us say it may have a camera. Camera is a kind of sensor, right? Or it may have some motion sensors. It may have some vacancy sensors, right? It may have some movement, no? Or you can also have it has some sonars which will help it to. It is also a kind of sensor. Now these are all examples of sensors. Now action means what? For example, one action, let me call it as move forward, is one action. This is one particular action which has to be done by the robot. Or let me give one more action, turn. This is another action that has to be done by the robot. So I said a robot or an agent will have sensors and it will also have some set of actions. Why sensors are required? Sensors are required because it has to observe. What it has to observe the state of its environment. After observing what, it will not sit quiet, right? It has to take some action. So this set of actions is going to alter the state. That means it is moving from one state to another state. For that, it requires sensors, right? So when I say examples of sensors are cameras, sonars, these are all examples of sensor. So what is the action? Examples for action: let's say move forward is an action, turn is an action. These are all actions. Now, what is the task now? What is the task of the robo? It has to learn. Robo has to learn a control strategy. Or when I say control strategy, it is nothing but it has to learn some kind of a policy. What policy? What is this policy for? It has to learn a policy for choosing the actions. Choosing the actions to achieve the goals. There are so many actions are there. Move forward is one action, turn is one action, left is one, turn right is one action, move backward is one action. These are all different actions. Now the robo has to learn a policy. It has to learn some strategy so that it can choose the proper action. Whether it has to choose move forward or whether it has to choose move backward. Whether it has to choose turn right or whether it has to choose turn left in order to achieve its goals. That is what a robo has to learn. Or let us say it has to connect itself to a charger when its battery level is low. That is also a action that it has to do. Right? So in this particular concept of chapter of reinforcement learning, this is concerned with how these robots are going to learn these policies, so that by experimenting in their environment. That is what we are going to learn in this reinforcement learning. Any doubt so far? Right? So that is what we are learning. As I said, we are going to consider an example of building a learning robo. A robo is also nothing but an agent. When I say a robo or an agent, a robo will have sensors. It will also have some set of actions. Why these sensors are used? Sensors are used so that it can observe its state, or it can observe the state of its environment. And then it is also provided with certain actions. Why these actions are required? Based on the environment, it has to choose a particular action so that the state gets altered. Examples of sensors: as I said, camera is an example of a sensor, sonar is an example. Actions are what? Move forward, move backward can be an action, turn right, turn left. These are all nothing but examples of action. Now, what this robo has to learn? This robo has to learn a policy for choosing the actions in order to achieve the goals. There are so many actions. You have a set of actions. Which action it has to choose? Whether it has to move forward or whether it has to move backward. That is a decision this robo has to take, right? In order to achieve its goal. So, here in this particular chapter, we are going to learn how these robots can learn successful policies by experimenting in the environment. Right? Any doubt so far? Okay. Now, how do you define this goals of the robot or the goals of the agent? Now, this goals of this agent is defined in terms of a reward function. That means reward means what? You are going to assign a numerical value, some kind of a numerical value, or you call it as a payoff, an immediate payoff to each action that the robo is going to take in order to move from one. See, it is in a but initial state. Let us take an example: TV. Let us say we all have TV at home, right? TV is switched off, right? When it is in the off state, that means it is in some kind of initial state. That is the off state. Off means it is switched off, right? That is one particular state. Now, you are moving, you have to change this particular state. Let us say you move to the TV is switched on, you go to the on state. How did you go from this off state to the on state? Let us say you switched on some, you provided the power supply, right? So you are doing, this is nothing but your action here. You are switching on this switch, right? So your TV is moving from the off state to the on state. Off is a different state, on is a different state. But to move from this particular off to on, what did you do? You did some action. What was that action? You switched on the power. Correct? So, like this, the robo will also be given a set of actions: switch on, switch off, move forward, left, right, all these kind of different sets of action are there. But what action it has to choose? It has to learn that. It has to learn what action, it has to learn some policy based on which it can try to choose this particular action. Okay, so as I said, it has to, let us, whenever you are so I told you that whenever it has, in order to achieve its goal, it has to choose the action so that it can move towards the goal. Goals of the robo are always defined by a reward function. Reward means what? It is, you are going to assign some numerical value for every action that is taken by the robo. When I say numerical value, it is nothing but a immediate payoff, okay, for each distinct action your robo is going to take to move from one state to another state, right? So the, let us say the robo has to connect itself to a battery charger. So when that is done, you are going to assign a positive reward. Positive reward means either you can some kind of a numerical value. Either you assign 100, you assign 0, something like that. Okay. So this reward function must be built into the robo, or it should be known only to the external person. So this task of this robo is what now? To perform sequence of actions, observe their consequence, and then learn a control policy. Control policy is one that from any, that's what I said, from any initial state, you choose the actions that is going to maximize the reward. I go on accumulating the reward. For every action, let us say I have taken first action. For first action, I am assigned 5 points. Second action I take, I am assigned 10 points. Then third action I take, I am assigned 15 points. These are all nothing but the, we call it here, in this case, we call it as the reward points. So what do? I go on accumulating all these points. Totally, I am having, let us say, 30 points. Okay, so when the robo, when it moves from one state to another state, it has to choose the actions in such a way that the reward is getting maximized. That should be the goal. So when I, which action can I take so that I will get the maximum reward? Right? So the control policy, the robo has to learn is from any initial state, chooses the action. It will choose such an action that will maximize the reward accumulated over the time. So over the time, I should see how much, what is the maximum that I can gain? What is the maximum points that I can gain? Okay, let us try to show, I'll try to show this in the pictorial form now. 1 minute. Okay, now let us say this is the robo, or I can call it as agent. As I told you, robo is also called as a agent. And then we have the, this is the environment. Environment means what? The surroundings in which you are trying to place the robo. And then okay, now this is a robo, an agent, or this is your agent, or I can call the agent also as a robo. It is interacting with the environment, right? So this agent, it is existing in an environment which is described by some set of possible states. As I told you, when we say TV is in off state, it is in on state. To move from off to on, you are providing the power supply, right? That's an example of change of state. How that transition happens? Because you are doing some action there. So here, this agent it's interacting with an environment which is described by some set of possible states. Let me call that as capital S. Okay, it can perform any set of possible actions. There are two things here you should understand. One is the set of states in which what are all the possible states. The another one is the set of all possible actions that the robo can take, that I call it as A. Okay, each time it is going to perform an action, let me call it as AT at any point time, no? So I am calling this at any time, it will take some action. So that I am denoting here as AT. In some particular state, ST. That means the robo is in this particular state, ST. When it is in this particular state, let me write it here. When it is in S0, S0 is the state in which it is in. It moves to the state S1. But how does it move? It does the action A0 in order to move from S0 to S1. Okay. Now, when it performs an action in this particular, when it has performed the action A0, correct? In order to move from S0 to S1, it has performed the action A0. So the agent will receive a reward for this. As I said, some points are assigned whenever you perform this particular action. So when now that you have moved, the robo has moved to S1. Again, it has to now, let us say, move to S2. In order to move to S2, it will perform another action A1 for which it will receive, let's say, R1. Again, it will move to another state S3 for which it will perform an action A2 and it will receive a reward R2 and this will continue. It can perform any of a set of possible actions. Out of, I said, we have a set of possible states. Yes. We have a set of possible actions. A. It can move from this possible set of states means what? S is going to contain something like this. S1, S2, S3. These are all possible states in which the robo can be there. And then you have the set of possible actions. These are all possible actions. As I told you previously, possible actions means what are the possible actions? Turn left, turn right, go up, go down, go forward, move backward. These are all possible set of actions. It has to choose the most appropriate action from this particular set. Right? Similarly, states also can be different. As I said, you are in the idle state, you are in the on state, you are in the off state. So these are all possible different states. So from one state, it is moving to another state by performing a certain action. And when it performs, each time it performs an action, the agent receives a reward RT. If I call it as in general, let me say RT. This indicates what? It indicates an immediate value, some kind of a payoff that the for this state transition. Look here, this state action transition. There is a state, you are moving to a different state. That means there is a transition there. For this transition, you are performing this, the robo basically is performing this particular action for which it will receive this reward R0. So this is going to produce a sequence of states, SI, actions AI, immediate rewards RI. So all this, you have so many states, sequence of states, SI, you have a sequence of actions, one after the other, actions are performed. You're also going to get rewards one after the other. You are getting the rewards. That is what is the task of this robo. Okay, now what is this task? What is the task that the robo has to learn now? It has, as I already told you, it has to learn a control policy. It has to learn some particular function. What is this control policy? That means it has to decide which action it has to perform. so that it is going to get the maximum reward. Obviously, everybody will want to have maximum reward optimization, right? You need to have, you want to get, if there is a choice between 25 rupees, 50 rupees, 100 rupees, if somebody is going to reward you, you will always aim for what? 100, because that is the maximum. Similarly, here, the robo, it has to learn a policy so that it can, maximize, or it can get the maximum reward. This control policy, we define it as pi s to a. Okay. It has to learn this policy. I'm just calling this function. This is a function pi. Instead of f, I'm calling it as pi. That's all. I'm mapping state to actions. Every time I move from one state to another state means I have to perform some action for which I'm going to get some reward. So I have to learn a function. The robo has to learn a function so that it gets to choose the appropriate actions so that it can reach its goal by getting the maximum points or maximum reward. So we will define a function. The goal is what? It has to learn a function. I'll define a function like this: R naught plus gamma into R1 plus gamma square into R2, and so on. It will go on where your 0 is less than equal to gamma, less than or equal to 1. Gamma is a constant here. Any doubts till here? So it has to learn a control policy. This is the function that we have defined. The machine has to, or the robo has to learn this function. Look here, we have put this particular function. S is mapped to A. S is a set of states. A is a set of action. That means every time you want to move from one state to another state, there is some action performed in order to move. Which action it has to perform? It has to choose appropriately. That is what it has to learn, so that it gets the maximum reward. Okay, that it is control policy is what? It outputs an appropriate action. That means it has to learn a proper action A from this particular set, capital. Any doubts, anyone so far? That is what the robo has to learn now. Now, before we proceed, this all this we are going to do based on this reinforcement learning. Okay, this reinforcement learning problem, it differs from other function approximation tasks. That means, what is so many functions or so many approximation tasks or algorithms we have learned so far? How does this reinforcement learning is going to be different from the other program? There are four important points that you will have to note down. One is called the delayed reward. I told you already that what is the task of the robo? It has to learn this target function pi. We have already defined this target function, which is mapping the state to the optimal action. I can also write this as A is equal to pi of S. That means, depending on the state in which you are going to choose an appropriate action for which the robo will be given a certain award. This is what it has to learn. Okay. Now, in case of reinforcement learning, the training information is not available in this particular form. Always we see what? We have always seen the data set is always given of this form, right? So far, whatever algorithms we have learned, we have always seen we have an instance in the last column, we are also providing it with the target concept, correct? But in case of reinforcement learning, if I put the same thing in the same form, look here, I have written it like this. But the data is not given in this particular form in the reinforcement learning. Instead, how do you provide then? How do you provide this data to the robo? We provide only a sequence of rewards. reward values. Okay, what are the values that are assigned? That is all you are going to provide. As it executes its sequence of action, you are going to provide the machine or provide the robot with the reward values. Now this will result in a problem called as temporal credit assignment. Okay, what is this? You are trying to determine which of the actions, as I said, there is a set of actions, correct? Which of these actions are to be provided with proper reward. That is what you call it as this temporal credit assignment, delayed reward. This is the concept of delayed reward, wherein you are not providing the trainer with this kind of a data x comma f of x, but you are trying to provide it with s comma sorry, you are not providing it with this kind of data, but you are trying to tell what are the sequence of reward values that are given to the machine as and when they go on executing the actions. Okay, that is your first point. The second point we are trying to see here is exploration. What do we mean by this? Now, one second, I'll just change the paper. The second point that we are going to learn here is exploration. Now, here the question, there are so many training examples, right? The question here is which of these experimentation strategy is going to produce the most effective learning. That means the learner who is a learner here, the robot or the agent is a learner. There is always a trade-off in whether should I choose or should I what to say consider choosing the exploration of unknown states and actions. That means I'm trying to find out something new, some new information, or should I go and exploit the states and action that is already learned with the high reward? What is my objective? This is one second. The second point is what we are going to. Second point, first point is delayed reward. Second point is exploration. Exploration means there is always a trade-off for the robot. What is the trade-off there? Whether it has to explore, the point is called as exploration, right? Whether it has to find out or explore unknown states in action. That means those states and those actions which it has never initiated before. That means you are trying to find out something new. You are trying to gather some new information. Whether should I go for moving from one new state to a new another new state by performing a new action? Should I do that, or consider the states and action that has already been learned? That means I've already taken this particular action to move from a known state to a known state, right? This I know very well is going to give me high reward. I know this action, that means I've already done, so I know it is going to give me high reward. But this is unknown. I don't know. Even if I take this particular state, new state, and a new action, I don't know how much of reward I may get. I may get maximum or I may get very least, right? So I do not know. So that is a trade-off that the robo will keep facing, whether to explore new states and action, in other words, whether to explore to gather new information, or go on doing whatever I've already done because I know very well that I'm going to get the maximum reward, right? Because the goal is what? You have to maximize the cumulative reward. I go on collecting rewards. As I told you, you have 25 rupees, 50 rupees, and 100 rupees as a reward, let us say. What you will aim for, you will always aim for 100 rupees, right? You want to always go for the maximum one. That is your second point. The third point is partially observable states. Now, generally we assume what? That the sensors can see the entire state at each time step, right? But what happens is in practical situations, sensors will always provide only partial information. For example, if a robot with a, let us say it has a forward pointing camera, it cannot see what is behind it, right? In such cases, it may be necessary to consider previous observation together with its sensor data. That means partially observable statements. Most of the time, we always assume that the robos sensors, it is able to see the entire surroundings. That is what we assume. But practically speaking, that is not the case. You cannot get the entire picture of of the surroundings of the robot. That's not possible. For example, if it has a front facing camera, let us say, suppose it has a robo has a front facing camera. Okay, then what it can take picture of? It can only take picture of what is in front of it, obviously, right? It can't take whatever is behind it. So then what you have to do in that case? So it has to consider the previous observations. Suppose in the previous observation or the previous action, it has made use of its back camera and then it has taken. So now you are trying to see only the front. Use your previous observation where we have already seen the what is there in the surroundings at the behind, and then try to choose your actions based on these. That is what we say partially observable states. Okay, always, but whenever we think of robo, whenever we think of a sensor, what do we think? Okay, it has a sensor, it is going to give us the entire scenario of its surroundings. That is what we think, right? But that is practically that is not the case. That's why example I gave. If a robo has a front facing camera, can it see behind what is behind it? It cannot see. Correct. So that means what? It is only going to give you pictures of. It is only going to consider what is there in front. But then, if I have to choose an appropriate action, the robot should also know what is behind. Correct. So what it will do? It will take into consideration the previous observations. What are the previous observations? Somewhere previous observation it would have used to the back camera and it already knows what is there behind. So in that case, it can try to take that also into consideration so that it can choose the appropriate action. Choosing appropriate action is most important. Only then I will get the maximum reward, right? That is the third point. The fourth point is lifelong learning. Okay, what is this lifelong learning? Now, this robo will always learn several tasks within the same environment using the same sensors. Okay, uh, for example, it has to learn many things. You cannot say, okay, move forward, but it will simply learn to move forward only. No, it has to learn so many things using the same front face camera. It is not only learning to move front, it will also learn, for example, it may learn how to connect to the battery, how to navigate through the narrow corridors, how to pick up output from some laser printers, how to push a door, how to move into that room. All these things it has to learn using its front face camera. Right now, this setting it raises a possibility of using. That means it is also using its previously obtained experience or the knowledge to reduce simple complexity when you are learning. That means lifelong learning means what? One front face camera is there, right, for the robot. Now, using that, it is not for learning just one particular task of moving forward. It has to learn, keep learning. Using that, it has to keep learning lifelong. And using that particular sensor, it has to learn many things, not just move forward. How do I connect to battery? It should learn how to do that using this front face camera. Using this front face camera, it has to learn how to move, how to navigate through the narrow places, how to pick up some output, how to take some images, how to find out if there is any obstruction. All these things it has to learn using this front face camera. Okay, that means a robot has to learn several related tasks. within that same environment, using the same sensors. Using the same sensor means what? There is a front face camera. Using this camera, it has to learn many related things, not only say, okay, I will only move forward. Not like that. It has to learn to move forward. It has to learn to take images. It has to learn to check with any particular obstacles. It has to creep through, maybe try to pick up some other hindrance that is there. All this it has to learn using this particular same sensor. It has to use and it has to learn. Okay, so these are the four different points which indicate to us that reinforcement learning is completely different from the other tasks that we have been learning so far. The first one is delayed reward. In delayed reward, let me go back and explain to you. In delayed reward, what did I say? The training data is not given in this particular form, x comma f of x, or if I put it in terms of states and the function that we have defined here, s comma pi of s, it is not defined like this. Whereas we provide, the trainer is going to provide the information in terms of immediate rewards. If the robo is moving from one state to another state by taking a or choosing a particular action, then the reward is immediately given to that particular action. So that is how we are trying to provide the data for it to achieve its goal of maximizing its cumulative reward. That's the first point. Second point is what we said, it is exploration. Exploration means here what? The robo is always in a dilemma whether to choose a new action to move from one unknown state to another unknown state, and then you don't know there. So in that case, what will happen? The robo is unaware how much it is going to get reward, because reward, how much numerical points are assigned, is known only to the trainer. It is not known to the agent. So when it chooses an unknown action or a new action, tries to gather some new information, it is unaware of how much reward it is going to get. Whether that will be the maximum or whether it will be the least, it has no idea. But when it chooses the repeated actions, when it does the repeated actions, then since it has already done it and it has won some awards, it all reward, it knows that it is going to lead to a maximum reward. So the robo is always in a dilemma whether it has to take unknown states or it has to go and do the same repeated actions. That is what we call in this point called as exploration. The third point, it's partially observable states. So here generally what we assume, when a robo has a sensor, it tries to give us the a picture of the entire surrounding. That is what we assume, correct? Generally, whenever we say there is a robo, it has a sensor, it has a camera, so it will give you what all is there in the surroundings. That's what we assume. But what is the practical problem here? What is happening? Suppose it has a front face camera. It can only see what is happening in the front. It cannot see what is happening at the back. But to take some appropriate action, the robo also has to know what is behind, and then only it can choose a appropriate action to win the maximum reward, right? So what it does, it makes use of the previous observations. So sometime previously it would have made use of back camera to find out what is at the back, and then would have taken some appropriate actions. So now it will combine this front images with the previous observation and then choose a appropriate action. That is why we say partially observable states. And then the last point is lifelong learning. Lifelong learning means, as I told you, once a particular sensor is there in a certain state and the robo is in a certain state, it has to learn all the related tasks in that particular environment using the same sensor. It cannot say, okay, front face camera, I will use only for this purpose or moving forward. No, it has to learn all the related activities. Using a front face camera, there can be so many things at the the robo can learn, right? As I gave you some examples, it can move forward, it can take pictures, it can creep through narrow places, it can try to see if there is any hindrance or obstacle. These are all possible work that it can do. It can learn in using that one particular sensor. So that's why we say robo is always involved in some kind of lifelong learning, right? So these 4 points is an important question as well, as to what are the aspects with which your reinforcement learning is completely different from other approximation tasks. Then you have to write all these 4 points. Any doubt so far? Next, we will move on to, that's about an introduction to reinforcement learning. That means a robo, we are trying to consider building a learning robo, and that moves from one state to another state by taking some action. Whenever an action is taken, suitable reward is given to the robo. That is what is an introduction to your reinforcement learning. I have already told. Now, how does this learning happen? That is what we are going to learn in this learning task. How does it happen? That means, how does a learning happen means what? Learning, as I told, the robo has to learn some strategy, or it has to learn some policy based on which it is going to choose its actions so that it gets the maximum reward. This is what it has to do, right? So how is this, how can we formulate this particular problem of learning these control strategies or the policies? We are going to formulate this problem based on a concept called Markov decision process, or in short we call it as MDP. Okay, we are going to formulate this problem. What is the problem? The robo has to learn a strategy or a policy based on which it can choose its action. So it has to choose such an action so that it gets a cumulative maximum reward, or numerical points are accumulated, right? So this problem of learning, we are going to formulate using the process called as Markov decision process, or you call it as MDP. What happens here in case of MDP? Okay, so we are going to perceive this problem as a set yes. Okay, yes is what? It is a set of distinct states of the environment. Any environment you take, there are going to be a number of distinct possible states. So we take this S, capital S is nothing but a collection of distinct states. And then we consider one more set A, which is nothing but a set of actions that the agent can perform. Okay. Now, at each time step, I will call it as small t. At every time step means, let us say every 10 seconds or every 20 seconds. That is a time step. Okay. Every time step t, the agent means what? The robo. Robo is going to sense the current state. What is the current state? Let me call it as ST. Sensing, it will sense the current state. Then, based on this current state, it is going to choose a current action. I will call it as AT, and then it is going to perform that action. Okay. At any, listen carefully, at any particular state time step T, the agent is going to sense. It is going to sense the what is the current state. Based on the current state of the environment, it will choose a current action AT, and then once it has decided which action has to be performed, it will perform that action. Okay, then this is what will happen. How does the environment respond? The environment now, what it has to do? It has to respond by giving the agent a reward. A reward has to be given. Let me call that as RT. RT is equal to, I can write this like that. That means A reward is given whenever an action is performed, AT is performed, sensing the current state ST. And you also, once you perform this, you are in ST, current state, you are trying to choose an action AT and you are performing it. So what happens? You are moving to the next state. From the current state, when you perform this action AT, you move to the next state. Correct? So that next state, I can call it as ST plus 1. This is nothing but delta of, I can write it as ST comma 80. So in this case of what is ST plus 1? ST, that means you are moved to the next state. How did you move? You moved from the current state ST by performing this action AT, you have moved to the next state ST plus 1. Now, in case of MDP or the Markov decision process, this delta of ST comma AT and R of ST comma AT, okay, they depend only on the current state and not on any other earlier state. We don't consider any previous observations here. Whatever is the current state, based on that, it chooses an action AT and then performs this action. Once the action is performed, what will happen? It is moving to the next state, which I am showing it as ST plus 1. So what this agent or the robo has to learn? It has to learn a policy. We have already defined this. Function f, I am trying to define it in terms of pi. Okay, from S to A. For selecting its next action, I have to select the next action AT based on the current state ST. That is, pi of ST is nothing but AT. Now, how can I specify this pi? How should the robo learn this function which I am trying to show it as pi? That is what is the learning task here. Any doubts here so far? I said we are formulating this problem of the agent has to learn, right? How are we formulating this problem? We are formulating the problem using the concept of Markov decision process or MDP. In MDP, how do we perceive this entire situation in terms of MDP? In MDP, the agent, the robo sees the set of states. We are showing it as capital S. It is nothing but the set of all possible states in its environment. And then we are defining another set A, which is nothing but the set of actions that it can perform. Okay. Now at each time step, what next I told? At each time step T, the agent is going to sense the current state. Current state, I am showing it as ST. Whatever is the state it is in, which it is in, it has to choose a appropriate action AT so that it can move to the next state, which I call it as ST plus 1. Okay, this is what the robo or the agent does. It will sense the current state, takes a suitable action, moves to the next state. When it does this, what does the environment do in return? It has to provide respond. The environment has to respond, right? How does it respond? It responds by giving the agent a certain reward. So how do I call this reward? I call it as R of ST comma AT. That means that is a reward which is given for moving from the current state ST and for performing this particular action AT. That's how we are trying to represent this. And then once you move, once you have chosen this particular action, sensing the current state, what happens? You are actually moving to the next state. You are not at the same point, right? You are moving, the robo will move to the next point because it has taken that action, it has moved to the next point. That I am showing the next state. So you are already into the, robo is already into the next state, which I am showing here as ST plus 1. So ST plus 1 is equal to, we are used to delta here, ST comma 80. So it has to learn now. So that means we have used here two functions. You observe here. One is which shows the next state, the st plus 1. I have shown it as delta of st comma at, and then I have shown r of, well, this indicates the, what does this indicate? It indicates the reward that is given. This indicates what? It indicates the next state. Both this, in case of MDP, these two functions depend only on the current state, but they don't depend on any of the earlier states or actions. That is, we are not considering any kind of what to say, previous observations. We are not considering it. Both these functions in terms of MDP, when you try to apply that concept, we are considering only in terms of the current state. All right. Now, as I told you, now the agent has to learn this pi. Pi is a function which is mapping the set of states to the set of actions, which I have also written it like this. Look here, this way also you can write that. Now we have to specify how can we train the agent this particular function, for what state, what action it has to choose. That is what it has to learn. So how can we formulate this pi, or how can we formulate this function? That is what we learn now. 1 second. Let me change this page. Okay. So how should we formulate or consider this particular function pi? What is our approach? What approach should we consider? Now, whatever policy we are going to choose, right? What is the goal? It has to produce the maximum possible reward for the robot. We have to choose such a function, correct? This pi has to be formulated in such a way that it produces the greatest possible cumulative reward for the robot over the time. Every time it does an action, it is going to get some rewards. And at the end, you should see over the time means as you go on doing, you should have got the maximum possible reward. Okay. How do we state this requirement? In order to achieve this requirement, we define what is called as a cumulative value, which I represent it like this: capital V to the power of pi st. This is the cumulative value. Cumulative means what? You go on adding it. That is what is called as cumulative. This is a cumulative value. We define this cumulative value, which is achieved by following this particular policy. We are trying to formulate a policy called pi. That is a function. Okay, from an arbitrary initial state. Let me put down that. So I define this function or cumulative value like this: RT plus, take a constant there, t plus 1 plus, this is square, RT plus 2 and so on. This I can write it as we move from I is equal to 0 to infinity, gamma to the power of I, RT plus I, to call this as equation 1. T plus I it is. Okay, what is this? It is nothing but we are defining a cumulative value. This is my goal. I want to achieve the maximum reward points at the end. I go on adding. First action I get 2 points, second action I get 5 points, fourth action I get 100 points, I know, 10 points, 20 points. Like that I go on adding. So at the end I should have got the optimal maximum points I should have achieved. So how do I state this requirement? That is my requirement. What is my requirement? I have to get the maximum reward points at the end. That's my requirement. How do I do it? I state, to achieve that, I define this called as cumulative value. How do I define this? Look at this. RT plus, we have put gamma as a constant there. RT, I'm in class. T plus 1 plus gamma square, RT plus 2 and so on. Right? Now, what is this? This RT plus, look at this, summation of I is equal to 0 to infinity, gamma to the power of I, RT plus I. This RT plus I is nothing but the sequence of rewards that is generated. Sequence of rewards. First, look at here, RT. This I am getting at the first state. For the first state, when I perform the first action, I get the first reward, that is RT. Okay. For the next second state, what I am doing, I am getting another reward, that is nothing but RT plus 1. Third time, what I am doing, I am getting RT plus 2. So this, when I try to take the summation, I can write it as RT plus I, which is nothing but the sequence of rewards that the robo has got, or the sequence of reward generated beginning from the first state ST, and you go on repeatedly performing this function pi. Why do you perform this function? In order to select the actions. You want to select the actions. Let's say AT is equal to pi of ST. That's where you select the action, so that your next action will be pi of ST plus 1. Now, here we have used a constant which is called as gamma. This is nothing but as I said, it is a constant value. Okay, this is going to determine whether your reward is immediate or it is a delayed reward. That is what your gamma is going to be determining. Suppose that means if your gamma here, if you see here, gamma is 0 there. Gamma to the power of 0. That means that is a immediate reward, because you are getting it for the first state. It is an immediate reward. Next, what happens here, gamma is 1. Gamma to the power of 1. Gamma is 1. Now, let us say gamma to the power of 1. That means for the next state, you are getting some, you also call this gamma as a discounted value. You are getting some extra there, something. Gamma square, you get something really more. That means if you set gamma is equal to 0, then only if I set gamma itself as 0, what will happen? If I set gamma as 0, only this much is considered. Only the immediate, because you don't have gamma here. So only the immediate reward is considered. As we set gamma closer to 1, okay, the future rewards are given greater emphasis. That's why we call this as discounted cumulative reward. Right? Let me stop here. Do you all follow something? I don't know. Nobody responds. Nobody asks any doubts. Only for attendance you will all answer. That's really very bad. That is what happens in this online class. Also can't help. Asta?
Yes, ma'am.
Very good. Abhinav? Abhinav? Aishwarya?
Present, ma'am.
Amrish?
Ambrish.
Anu? Arba?
Present, ma'am.
Yes, ma'am.
Present, ma'am. Present, ma'am.
Ashok?
Present, ma'am.
Benita?
Present, ma'am.
Ravi?
Present, ma'am. Yes,
Nivisha?
ma'am.
Chaitra?
Present, ma'am.
Daimalya?
Present, ma'am.
Diksha?
Present, ma'am.
Deepika?
Present, ma'am.
Emmy?
Present,
Krishna?
ma'am.
Gangubai?
Present, ma'am.
Priya?
Present, ma'am.
Harshit?
Present, ma'am.
Ginger?
Present, ma'am.
Kavya?
Present, ma'am.
Kishore? Kishore is not there. Lata,
Yes, ma'am.
Manisha,
Yes, ma'am.
Manjunath,
Yes, ma'am.
Naina,
Yes, ma'am.
Nilanjan,
Yes, ma'am.
Nishant, Pavitra,
Present, ma'am.
Maithili,
Present, ma'am.
Present, ma'am.
Priyanka,
Present, ma'am.
Pavan,
Present, ma'am.
Akash,
Present, ma'am.
Shari,
Present, ma'am.
Rakesh,
Present, ma'am.
Ramya,
Present, ma'am.
Lakshmi,
Present, ma'am.
Ravishankar,
Yes, ma'am.
Rizwan,
Present, ma'am.
Chal,
Present, ma'am.
Savita,
Yes, ma'am.
Preeti,
Present, ma'am.
Sneha,
Yes, ma'am.
Spurti,
Present, ma'am.
Srinidhi,
Present, ma'am.
Srinivas,
Present, ma'am.
Sunil, Vaishnavi,
Present, ma'am.
Vinny, Vinny.
Present, ma'am.
Thank you.
Ma'am, Arjun present, ma'am. You didn't call my name.
I called your name. You didn't answer.
Ma'am, seriously, no, ma'am. I didn't get.